Okay, so today's plan is to cover a chapter of scattering. So there are two important topics. One is about the Born approximation. Another one is partial wave and phase shift. I believe you have done some homework problems about those two topics. And today's first, I would like to go through some very briefly about the concepts related to the Born approximation, and then I also will go through the concepts about partial wave and phase shift in more detail, and then I will do two problems about this kind of a partial wave and phase shift, and show you guys how to determine the phase shift. As usual, feel free to stop me whenever you want and feel free to ask questions. Okay, so let's talk about Born approximation. First, let's look at the setup of this problem. Okay, basically, the Hamiltonian is the free part plus scattering potential. And we always assume the scattering potential is localized at some places. And imagine you have an incoming wave, which is a plane wave, labeled by the momentum k. Let's call it as a cat phi. And with energy, is h bar square k squared divided by 2m. Now we're interested in the scattering state, right? So we want to look for the scattering state of this problem, like of this Hamiltonian. We know there's a general formula for this kind of a scattering state known as the Lippmann's Schroeder formula, equation, whatever. Plus, I think it's something like this. Right? So this is one of the most important equation in the scattering theory. So this is the scattering scattering state we are looking for, and this is just the incoming state, which is a plane wave. By iteration, we know we can write down. By the way, let's call this guy as g because it's a Green's function, right? So it's g v phi plus g v phi plus dot. So you can factor out this incoming wave. So it's like gv plus gv, gv plus gv, gv. So in principle, you can solve this incoming, this scattering state in terms of the incoming wave and this Green's function and the scattering potential. Okay, so if you let's still look at the first line. If we can write this guy in the real space representation, right? I believe you're familiar with this. I just repeat this for. Okay, so this is the scattering. This is the incoming wave, and yeah, I just copied from this Sakura book. R prime, the R prime. This is the Green's function. Basically, the free propagator, right? R prime. Yeah. So this is the Lippmann-Schroeder equation in real space representation. On the other hand, we know that at infinity, Okay, so let's look at this kind of scattering problem. This is the incoming wave. If we look at some point that's far away from the scattering potential, we know this potential must be able to retain in terms of this kind of plane wave, which is a corresponding to the incoming one, plus outgoing spherical wave, right? K prime, so K and K prime. So K prime is nothing but K, the magnitude of the momentum times r hat pointing from the scattering potential to the point we're looking at. So this quantity is known as the scattering amplitude, and the square of this guy is nothing but the cross section, right? And very roughly speaking, you can understand this quantity as the probability that the incoming wave being scattered into this direction. Or it's like the probability that you can find a particle in this direction. And that's what we measure in experiment. And therefore, to match our theory with the experimental result, so the quantity we need to calculate is this cross section, basically this f function, right? And so now we only need to find the expression for this f function, this scattering amplitude, in terms of this kind of quantities we know from our theory. Basically, is the scattering potential or the Green's function or some, right? So how to do that? We know the general expression, and we just need to take r goes to infinity and compare this expression with this guy. And we can rid of the expression for the f. That's basically we do, right? And eventually we find, if we do that process, I believe you did this in the class. I just write down it directly. Minus 2, so very, by the way, correct me if I did something wrong. Right? It's proportional to this guy. So this bra is just a plane wave. This phi is the, phi is what? Phi is the scattering scattering state. V is the scattering potential. So what's this guy? This guy, if we know what is V acting on phi, then we can calculate this f, right? So okay, let us make use of this use this equation. So here you can say, oops, to obtain this expression, we just need to activate the scattering potential on this state phi. So you get a V. So you get a V phi plus VG V phi plus dot dot. So if we only keep the first term, it's known as the first order Born approximation. If we were to keep the second order, it's the second order Born approximation. So you can say we can calculate this f function from this expression, which is k prime v. By the way, this phi is nothing but the k, the incoming plane wave. K plus k prime v g v k. Yeah. So once we have this formula, we just need to do some integrals, and then we get the result, and we can compare our theoretical result with experimental data, and that's it. And by the way, the physical meaning of these kind of terms are also very clear, right? Because imagine you have a scattering potential. This is your incoming wave. You encounter some scattering potential V, and then you scattered out. So, oops. So you scattered once. If we look at the first order approximation, if we look at the second order approximation, um, you have an incoming wave, K. You encounter a scattered potential V, and then you free propagate for some time, which is a free propagator G, and then you encounter a potential V, and then you scatter out. Right? And you can keep going, like add more terms, and the physical process was the same. Yeah, that's all I want to say about about the Born approximation. Is it clear, or any questions about this part?
AG.
Uh-huh.
One very small question. So the way that you've kind of defined some of the notation, then you're saying ket k is equal to the same thing as ket phi.
You
Are
mean
they
here?
completely identical?
Yeah, this is because how we set up our problem, right? Like
Yeah. Okay.
yeah, yeah, yeah.
Thank you.
Sure. Right. So this is the Born approximation. Yeah, I believe you guys are familiar with this. I just refresh your memory, like yeah, for completeness, I guess. So for the now let's look at the partial wave. And phase shift. So first, I would give you also a very brief kind of picture what's going on for this partial wave, and then I will introduce the like how we determine the phase shift, and do go through two problems to show you guys how to carry it out explicitly. Right? Okay, so whenever we talk about partial wave, we always needs to assume the system is symmetric invariant. Right? Basically, our Hamiltonian commute with L square and also commute with LZ. This is a one, by the way, this basically means the potential only depends on the magnitude of the radial variable R. That also means the scattering state, which is our goal. Remember, our goal is to find the scattering state of the problem. This guy can be expanded in this kind of form. Something like this, right? Because of this symmetry. Okay, so now the same setup, right? We have some scattering potential, we have an incoming wave, assuming this direction is a z direction, and we have some outgoing wave, right? And also we look at some points at infinity far away from the scattering potential. And then we know from physics, we know this guy must be able to retain in terms of this form, the incoming part, and also the outgoing plane wave, right? which is f k prime k r expansion I k r. This guy, because of the symmetry, we know the argument only depends on the theta. Theta is the angle between the z direction and the r direction, which makes sense because the system is symmetric, it's kind of axial symmetric around the z-axis, right? Now, like as we mentioned before, this guy, we can also do a expansion into kind of a decompose this f theta function into different sectors labeled by the quantum number L. 0 to infinity, 2L plus 1. This 2L plus 1 just for convenience. Something like this, right? Of course, it's always convenient to express the whole function into different sectors labeled by L, meaning that we also want to kind of expand this guy in terms of this L. You can do that. I believe it was done in the past. Then we can write this wave function in terms of the L like into different sectors, which is 2L plus 1. Okay. Yeah, you can also find this expression in the Sakura book. One plus 2 IKFL R expansion IKR GL right. So what we have done so far? So what we have done so far is nothing but utilize this symmetry, this axial symmetry, right? Basically, we know the expression of this wave function at a position that far away from the scattering potential, right? This is well known. And because of this symmetry, we can write this wave function kind of into different sectors labeled by L in this form. So originally, all the scattering information is contained in this F, right? Remember F, K, K prime, which is known as the scattering amplitude. Now, all the information contains in this FL, right? All the scattering information contains in this FL. Basically, we only need to calculate this FL. Okay, so another thing we need to know is the number of particles is conserved, meaning that the incoming wave, the magnitude of the incoming wave should equal to the magnitude of the outcoming wave. So this corresponding to the incoming one, this corresponding to the outgoing one, right? And this is the outgoing. The particle is conserved, meaning that the square of the coefficients should be the same. That means this guy must be square to 1, meaning that this guy can be only a phase factor. That's how we introduce the so-called phase shift. Let's just rewrite this. So basically, it tells you the outgoing wave has only a phase difference compared with the incoming wave, like a spherical incoming wave.
Could you explain one more time how we see that as a phase factor
Okay,
in the
sure.
equation where you circled it?
Right. So basically, this guy, the first term is the outgoing spherical wave. Sorry, incoming spherical wave, right? It's minus IKL. And this guy stands for the outgoing spherical wave. We know the total number of particles is conserved, meaning that there's no particle at infinity. It's like outgoing should be equal to incoming, meaning that the probability, like this, meaning that this guy, the square of this guy should be equal to the square of this guy. And this guy square to 1 tells us the whole prefactor here can be only a phase factor. And that's how we introduce this so-called phase shift delta L. Yeah. And then eventually we write in this form.
So are we wrapping up K dependence into delta L?
Exactly, yes.
Okay, but that's not a problem.
Yeah.
Okay.
Yes. Of course, it's K dependence. If you change the energy of an incident wave, the phase shift will change in general. Yeah, depends on your energy. Yeah, usually, like just suppress this K dependence. Yeah, it's K dependent. So what we have done so far is nothing but rewrite our wave function at infinity, in like kind of decompose the wave function into different sectors labeled by L, and introduce the concept of the phase shift delta L. So let me draw this relation. I think it might be useful for you guys. So basically, this scattering amplitude contains all the information, and then the F theta contains all the information, then FL contains the information, and the delta L contains the information, right? So all information about the scattering is encoded in the phase shift delta L, which is the phase shift between the incoming and ingoing and outgoing waves. So maybe I can write it down.
But what if can we have a potential which will I mean, if we're not thinking of particles or anything like that, but we're thinking of just regular classical waves, right? We can have some sort of damping inside of the potential, right? So the outgoing wave is smaller in magnitude than the incoming wave.
Right. That's. I mean, in real case, that can happen, but that's beyond the scheme of, of this discussion. Yeah. Yeah. There's some basic assumptions we need to obey. One is the energy conservation. We always assume that energy is E. We are looking for the basically we are solving this kind of a E H phi equal to E phi. E is the H bar square K square. So it's an inelastic scattering. And then we also assume there's no absorption of your particles. And yeah, that's basically the system is U1 symmetric. The total number of particles is conserved. Yeah, of course, if you assume your potential is there's an imaginary part and there will be some the total number of particles is not conserved anymore, and then we need to modify our theory. That's yeah. Any other questions? Okay, so that's how we introduce delta L. Delta L, the phase shift. Is it clear? Like so far, the logic here. Okay, so let's talk about how to determine the phase shift. Okay, so the general idea is following. By the way, we work with now we assume the potential is in this form. Some r smaller than r, there is some expression we don't know, but r larger than r, capital R, less than 0. Basically, there's some range of the potential, which is r. So now the basic task we need to do is solve this equation, this Schrodinger equation. And so how to find the phase shift is when we solve this equation, we need to separate our Schrodinger equation into two regimes. One is R larger than a capital R smaller than the capital R, and match the boundary condition at R equal to R, right? But there's another regime, which is R goes to infinity. So R goes to infinity, we know the expression, like what we discussed here, which is some expression that contains delta L, the phase shift. So basically there are two places we need to match the boundary condition. One is at R equal to capital R. Another place is R equal to infinity. So by matching those two boundary conditions, we can obtain the delta L. Okay, so let's do one step further. We basically match the boundary condition at the R at the infinity. Then we can transfer the delta L to the coefficients of the wave function in this regime. Some delta L dependence, right? And then match this boundary. By the way, the solution in this regime, to get the solution in this R smaller than capital R regime, we need to specify our potential, the form of potential. So we do this boundary match first, and then do this boundary match at R equal to capital R. That's how we usually approach this problem. Okay, so how do we, so at R, now let's look at this regime, R larger than outside this scattering potential. The wave function, sorry, the equation we need to solve is nothing but this. And this UL is R times ALR. ALR is the radian wave function of our total function phi, right? And of course, for R larger than the capital R, R, this V is 0, so there's no such term. The solution for this guy is given by the general solution. By the way, here I'm just stepping through like some details. If you, yeah, any questions, just let me know. Originally, I was planning like I just tell you the answer, but I think it might be useful to step through all the details. Then it's easier for you guys to read the Sakura book. And it's, by the way, it's in the Sakura's book. So. Here's some special spherical Bessel special function. I don't know what is it, but this guy is JL plus INL. This guy is JL plus minus I. C1 and C2 they are just coefficients. I know what is JL. The expression is actually very simple. It's, by the way, it's also the special, like a spherical Bessel function. Oh, something like this, I believe. Here I just write down for you. It's not very, complicated. It's something like this. So one expression, like one result you need to know is L equal to 0, which is X sine X. Yeah. I think it's good to remember this. It's very simple. Yeah, because in most cases we only care about a S wave scattering. Basically, we want to calculate the phase shift for L equal to 0. Then the only special function we need to deal with is these two, and they are not so special. They're just sine and cosine. Okay. Then because we know the radial wave function, we can write down the general solution for R larger than capital R, which is there are some prefactors that we can match, determined by matching with the plane wave solution, but let's forget about that. So this is a general solution. And now what we want to do is take the R goes to infinity, take the R to infinity. Basically, we need to approximate this guy with some expression, this guy with some expression, because when we take R to infinity, there's some expression we can use, and match the expression here with the expression we obtained in this place. Okay, whatever. Yeah. It's like this. Match our solution with this guy. And then by compare the coefficients, we can determine this C1 and C2 in terms of this phase shift delta L. Is it clear, like the general philosophy here, like what's going on here?
So
Yeah.
the reason this works is because this function that we calculated previously, we already assumed was for R was at infinity.
Exactly, yes.
Okay.
It's like from physics, we know at infinity how the wave function looks like. And we introduce the delta L, the phase shift. Then look at our Schrodinger equation. We can solve this Schrodinger equation for the R like larger than capital R. And then we match the boundary condition at infinity. Then somehow we transfer the delta L dependence to the wave function in the R larger than capital R. And then match boundary condition at the R equal to capital R and determine the phase shift. That's the philosophy. Yeah. And I think, okay, so okay. So the expression here we need to use is, I'm doing some very detailed stuff, but yeah, but I think it's useful. I hope you don't get lost in this kind of details. So whenever you feel lost, let me know. I can tell you what I'm doing here. So basically we need to use this guy and this guy. You already, oh, there's a minus sign. You can already say, this is the incoming spherical wave. This is the outgoing spherical wave. So we only need to match these coefficients with the coefficients here and determine the C1 and C2, right? So if you compare those two, we find the C1 is, and the C2 is this. This result is obtained by matching the boundary condition at infinity. And then, we can write this radial wave function. Remember, it's C1L. We are going to obtain the K expression we need to solve the partial wave problems. So I just replace this guy with the expression we obtained. This guy is 1/2. And remember, this guy is nothing but a linear position of JL and NL. This is also a linear position of JL and NL. So we can rewrite this guy in terms of JL and NL. Here's some very simple algebra you can do by yourself. Okay, so this is the K expression we need. Basically, now we express our radial wave function outside the scattering potential in terms of this the delta L, the phase shift. If we are able to solve the wave function within the potential, then we can match the boundary condition at the R equal to capital R. We can determine this delta L. That's all we need. Is it clear so far? Any questions or comments? Let me know. Okay, so it seems it's clear. So let me give you an example how to determine this delta L. Okay. To determine the delta L, we need to look at what is the AL, the radial wave function inside the scattering potential. Now, similarly, we need to solve the differential equation here, this guy, with some expression of the V. Let's look at a most trivial case, which is known as the hard sphere scattering, meaning that the potential inside the capital R is infinity. That tells us AL is 0, right? Because the potential is infinity, so the wave function is 0. Meaning that we only need to match the boundary condition at R equal to capital R. This tells us, delta IL, so cosine delta L, J L, K capital R minus sine delta L, N L, K capital R equal to 0. From this expression, we obtain that this tangent delta L equal to JL KR divided by NL KR. Right? Then this is the expression for delta L. This is a general expression without any approximation. We haven't done any approximation, right? Yeah, of course, you can assume the KR is much smaller than 1, meaning that only L equal to 0 is important in the scattering process. Then we only care about this delta 0. This very common, right? Then KR and 0, KR. Remember the expression, this guy is sine KR divided by KR. This guy is minus cosine KR divided by KR, which is minus times KR. Therefore, delta 0 equal to minus KR.
Oh, that's a much simpler result than what we were doing.
Yeah.
Okay, that's nice.
Yeah, whenever we focus on this kind of S-wave scattering, this kind of a special function becomes not that special. It's just the sine and the cosine. So the result looks very simple, right? And this also makes sense, right? Yeah. Let's look at another example.
Could you mention quickly one more time where the L equals 0 approximation comes from?
Oh, okay. L equals 0 approximation from this guy. K times capital R much smaller than 1, right? This because there's a upper bound where, okay, it's like a L should the maximum L should be smaller than KR. A very rough expression for this. Did you guys derive something like this in the class? Okay, so basically, okay, so the intuition is also very simple. Imagine we have R, and this is the income. This is a very semi-classical picture, but very intuitive. Yeah, it's not a very rigorous, but it's kind of give you some intuition. So I will not derive it rigorously, but just to give you this picture. Imagine I have a particle with momentum with momentum mv, and at distance, let's say a, we know that only a is smaller than a smaller than this r, it will scatter by the potential, right? Classically speaking. And now let me do some trick. Let's times mv times mv. This guy is nothing but the but h, but you can say this is nothing but the p. This is l. Sorry, this is r, right? R. This is nothing but p cross r, right? Because this r pointing in this direction, and p kind of perpendicular to this guy, so it's p cross r. So this is l in some sense. And what's this guy? This guy is, this is p. P is nothing, is k. So it's k times r. So you can say for this kind of only when your L is smaller than kr, it will be scattered. This is a very classical picture, but give you some intuition. Yeah, is it clear? Okay, yeah. Yeah, I believe, I think you can derive it very rigorously. If, yeah, it's also in the school, I believe. Yeah. Okay, so that's why if we assume the incoming wave has no energy, then we always only need to care about the S wave scattering. And we do this approximation, yeah, and we get this result. Yeah, actually there's another example I want to do, but it seems we are running out of time. Another more non-trivial example. This one is too trivial, right? Because this is 0, we only need to set this guy to be 0, and we determine the delta. But you say the general philosophy here, right? Okay, so let me very briefly sketch the problem, and we can end our discussion today. Okay, so the problem is this. We have some attractive potential, assuming V is larger than 0, V not larger than 0. So attractive potential, and solve the simple, like determine delta 0. Okay, let's say determine delta L, generally speaking. To do that, we also need to solve AL. Okay, let's okay, maybe I can, okay, oops. Let's determine delta 0. Okay, we only care about S wave. Then we write down this expression. To m h bar square v minus l plus 1 r square u l z. So for l equals 0, everything simplified. R square. This guy, it becomes this guy becomes 0. And let's call this guy as gamma square. So it's k square plus gamma square. Yeah. So this is a simple harmonic oscillator, right? So we know L0 equal to a sine squared k square plus gamma square r plus b cosine squared k square plus r gamma square r. On the other hand, we know there's a boundary condition, meaning that u r equal to 0 should equal to 0. So this term goes away. We only have this sine term. So there's a0 r equal to u0 r divided by r. So by solving the differential equation, we obtain the expression for the radial wave function inside the potential. And then we only need to match the boundary condition. This guy equal to the expression we obtained above. This guy, let's denote as A tilde equal to A tilde. And also, if you don't want to calculate this normalization factor, we can we also have this guy. The derivative should also continuous. And divide those two, you cancel out this normalization factor, and you get the expression of delta zero. You can determine that. By the way, you need to be careful when your potential is a delta potential. Then the derivative is not the same. There's another term, right? I think it's like a very standard. When you solve the one-dimensional problem in quantum A, you always have this issue. You have another term, some prefactor. Yeah. Then so any question? That's what I want to say. Yeah.
Yeah. So Sakurai made a kind of a big deal about matching this boundary condition using the logarithmic derivative, i.e. dividing the boundary conditions by each other.
Right.
Like, why does that work in general? Like, could you potentially be losing it? Like, are the boundary conditions overdoing it in terms of the information you have, such that dividing them retains all the information you need?
Right. Okay. So that one I believe is not true when your potential is delta function. In general, if your potential is finite, that's what we did here, right? We have this match the boundary condition. This is what was true. The wave function is what was continuous, and the first derivative is continuous if your potential is finite. Then you divide them. That's nothing but logarithmic derivative, right? Yeah. And if it's a delta potential, there another term in this derivative boundary mesh that will compromise the expression in the Sakura, right? So yeah, so that's why I say the most important expression is this guy, which is a radial wave function outside the scattering potential. Then give me a potential. I can always solve for the radial wave function within the scattering potential and then match the boundary condition. It's not difficult at all, right? It's just a match. You write down two equations, whatever, manipulate with them and get a phase shift. That's not a big deal. You don't need to memorize the like the complicated expression given in the Sakura. I also didn't remember. It's kind of a very complicated. That's yeah. Hope this helps. And any other questions?
Yeah. Hey G, I have a question. Could you go up just a teeny bit? Yeah. How did you know that function u goes to 0 at r equals 0? I don't know if that's obvious or not.
I believe that's one of the homework. Basically, your r times a l r 0 should equal to 0. This guy is what was true, I believe, in the radial, in the spherical coordinates. Yeah, this is what was true.
Okay.
Yeah, because when you go to the spherical coordinates, you introduce some singularity, meaning because you are dividing this r. So when you get some solve this equation, you may introduce some unphysical solutions. You need to impose some constraint to get rid of this kind of unphysical solutions. This is the constraint you need to impose, and yeah.
Thank you.
So yeah, this is a very good question actually.
Yeah, about this U vanishing and R equals 0, I remember professor talked about in class that you can effectively think of there being an infinite potential at r, like at r smaller than 0 in a real axis, so that, like, you know.
Okay,
or-
yeah, that's a good way to kind of physically understand it. Yeah.
But if we're just solving Schrodinger equation on a given range, is it like, can we always treat treat the potential of boundaries to be infinite? Like, what if it's a periodic boundary condition?
What do you mean by solving Schrodinger equation?
Because now we're just solving these UL, like basically it's an effective Schrodinger equation, right? About UL.
Right.
And we're solving it at the range r greater than 0.
Right.
But since we're not given any information about r smaller than 0, why can we assume that we can extend that to the whole real axis with the v equals infinity at r smaller than 0?
Okay, I guess that's just the, I mean, r smaller than 0 is an unphysical regime, right? You don't want to have any particle flow to that unphysical regime,
Okay.
I guess. Yeah, that's a good way to understand this boundary condition. Yeah, it's like r is from minus infinity to plus infinity. The only physical regime is r larger than 0. And you don't want to any particle within this unphysical stay in this unphysical regime. So this point must be 0, and yeah, some wave function stuff.
Yeah, and I have another question that, like in the assumption you get, you assume that, like, when r is larger than big R, then v is 0. But what if there is some like top potential where it just vanishes gradually? Where should we put this R?
Oh, okay. So that's another small section in Sakura. Yeah, I didn't touch up on. So you may read it by yourself, or if or I can do it next time.
So this will be different from what we did.
Yes, it's different here. You can say the whole discussion, like we discussed here, it depends on, we can separate this kind of stuff, the regime into two parts, and we can solve the part outside the potential very easily because the potential is 0. Then we can match the boundary condition at infinity. We get this nice result, this AL, this nice result. And then we solve the AL within the potential given once the potential is specific, once the potential is given, then match the boundary condition at R equal to capital R and get the delta L. That's the philosophy. But if you have some, like what you said, some this potential, it's not true, right? But I believe there's a formula we can calculate. We can make use of. Like it's in like the first homework in the homework 9, right? There's an expression for delta L equal to some delta B equal to some L divided by some length scale in your problem, or what I didn't remember exactly, but or K or divided by K, something like this, right? B, yeah, something like that, given in that section.
Thank you.
Sure. But for most of the problems, it looks like this, like what we have discussed here. This kind of form is kind of a, let's write it here. V R is 0 for R and everything. By the way, the homework 9 is the last homework, so you will have no homework next week. Yeah. Okay, so that's all I want to say, and yeah, so feel free to leave if you have no questions.